Now we can take a look at what energy is going to look like. So energy with the simple harmonic oscillator. So just like in all the other work we've been doing, the total amount of energy is going to equal K plus potential energy. And I'm going to not deal with the potential energy in our vertical spring. We'll keep our conversation to a horizontal spring and come back to that later. But if we have kinetic energy, then that's 1/2 mv squared, and then plus 1/2 kx squared would be the potential energy stored in the spring. But of course, these are going to oscillate back and forth, and the total energy will be constant, while the relative share of kinetic and potential is going to change based on the velocity and the position. So the sum of these together is equal to a constant. But we can also there's a couple of other ways to get at what the total energy is, and that's by looking at the extremes. So, so the energy is going to be equal to 1/2 k a squared at the endpoints, but it's also going to be equal to 1/2 m v max squared, and that's in the middle, where x equals 0. And then so it's pretty easy to see the relationship between Vmax and A. So there's more tools in your toolbox for problem solving. So now let's take what we know about simple harmonic motion and extend it to a new case. The physical pendulum is sort of like a regular pendulum. And if I'll just remind you really quick what that looked like. So here's our regular pendulum. We're hanging from the ceiling. We have an equilibrium point. We pull our pendulum back. And we know that there's going to be a torque that's exerted by gravity, mg, and this has a length L. And the perpendicular component that creates this torque is going to be mg sine theta. So when we went to do this, we said torque is equal to I times alpha, and the torque is equal to mass times gravity times the leverage, which is L sine theta. So mass, gravity, L sine theta, but that's really approximately equal to mgl theta for small theta. And then the rotational inertia for just a single mass is going to be ml squared. And then angular acceleration is the second derivative of the angle with respect to time. All right, good. And of course, there's lots of cancellation here. If we wanted to get the derivative, the differential all by itself, then we'd see that the m's cancel and one of the l's cancels. So m is gone, one of the l's is gone. And then I have G and L. And of course, there's a minus sign in here because there's a restoring force. So this is going to be equal to negative, and I've divided both sides by L. So negative G over L times theta. And then that means that our angular frequency is going to be equal to angular frequency squared is going to be equal to G over L. All right, so with any differential equation associated with simple harmonic motion, once we can get it down to the differential and set it equal to the displacement, then that means whatever coefficient is out front, that's omega squared. So with the physical pendulum, it's slightly different. And we have a long, thin rod, a meter stick in this case, but it's not rotating about the endpoint. It's rotating about some point here off center from the center of mass. So I'm going to call that parameter B, the distance from where it's oscillating to the center of mass. So here's the physical pendulum. I took a meter stick and I drilled some holes in it. And here's the 50 centimeter mark, and here's the axis of rotation. So when I pull it back and forth, I have a photogate down here, and I can use the photogate to determine what the period is. So the way you do it is you go start, stop. Notice how we have to let it swing back through so we get a complete cycle. So I'm going to share my screen now so we can take a look at our data logger. And we can see that it's all set for collecting data. So I'll set our pendulum into motion, try and get a few data points. All right, had to restart it. And there we go. We're getting some data points in. And it is the period. And you notice it looks pretty consistent. So I'm going to highlight this data and take the average. And you can see that the average is 1.662 seconds. The standard deviation is 0.0157. So that means I can have confidence in the data to probably the 100th decimal place. So I'm just going to write down 1.66. Okay, and I'm going to stop sharing now. And we'll come back and take a look at our notes. That's great. So here's our physical pendulum, and 1.66 seconds for the period. Now in this case, our B value, since I had a hole drilled at the 35 centimeter mark, 35, and then subtract that from 50 is going to give me 15 centimeters, or 0.15 meters. And so what we'd like to do is try and figure out what should the frequency be. So we have a couple of things at play. Number one is that I know that the center of mass for a long thin rod is going to be equal to 1 over 12 times ml squared. But now I'm oscillating something that's off center. So if you recall the parallel axis theorem, and this shows up a lot. It shows up very frequently on the AP exam. This is an easy way to get 5 points, is by applying the parallel axis theorem when appropriate. And so when we have, we want to find out what the rotational inertia is for something that's off axis, then we just take the center of mass, rotational inertia, and then add the mass times b squared. So that means we now know what the rotational inertia is. And we're going to apply a similar approach that we did over here, where we identify what the torque is. And in this case, the torque is created by gravity, the center of mass, and then set that equal to I alpha. And so we have a plan for figuring out what I is. And then alpha is just the second derivative. Now, before I go too far, it's a good reminder that frequency is equal to 1 over period. So I know what the frequency is. Do that in just a second. And so that's 0.602 hertz. So it means it doesn't hertz that much. And then omega is also frequency, but it's angular frequency, so it has units of pi, or radians rather. In order to get the radians, I'll need to multiply that by 2 pi. So 2 pi f, and so times 2 times pi. And that gives me 3.78. Radians per second. All right, now, this is what we got experimentally. We'd like to calculate theoretically what we should get for angular velocity, and that means we establish a differential equation which is represented by Newton's second law written as a torque equation. And the torque is going to be equal to mass times gravity again, sine theta again, mass times gravity, sine theta. But in this case, the L is going to be my B value. And then times the sine of theta. So we have a torque that's exerted here. And then we'll see what happens from there. So our torque is going to be equal to mass times gravity. And sine of the angle, but we'll do small angles. So I can just write down theta. And then the leverage is going to be indicated from the axis rotation to where the center of gravity is. So that's just going to be B. Now on the other side of the equation, I'm going to have I, and there'll be a minus sign here. Like that. So our next step is to do a little bit of algebra to try and get it into this form. And then whatever is this coefficient out in front of theta, that's what's going to be omega squared. So give this a try and then see how your angular velocity compares to the one we got experimentally, because this would be the thinking part of it. And then see what you get for omega, and you could do a percent error. All right, that's a good start. So let's chew on that for a little while. Now find omega. Find omega and percent error. Because this is theoretical. All right, that's it. All right, so the rest is for you to do. All right, good luck, and we'll talk about answers tomorrow.